and welcome everyone. We will be discussing the morphological properties for metal powders in general today, and we'll focus later on the laser melting additive manufacturing or 3D printing process and the importance of morphology for that process. To start with metal powders manufacturing, there are two distinct methods: direct reduction and three types of atomization. In direct reduction, metal oxides are reduced in the solid state by a carbonaceous source. The final powder is much more irregularly shaped, as you can see in the bottom photos, than the more spherical atomized powders, which allows higher green strength of compacts. In atomization, there are three types: gas, liquid, and centrifugal. In gas atomization, a turbulent stream of molten metal forms droplets as it cools in a surrounding gas chamber. In liquid atomization, a stream of metal is ejected at high velocity and intersected by a high-pressure liquid stream to speed droplet formation. More rapid cooling allows formation of finer particles than gas atomization, which has a lower limit of about 10 microns. They have generally wider distributions than gas atomized powder as well. In centrifugal atomization, the powder is compacted into a rod-shaped and into a rapidly rotating spindle hit by an electric arc, which liquefies and forms droplets which cool and are collected in a surrounding chamber. In powdered metal parts manufacturing, compaction includes die pressing and is used to form parts in a mold under high pressure. In hot isostatic pressing, compaction and sintering at high temperature take place simultaneously. In the sintering process, sintering only takes place in a furnace after cold compaction. Next, selective laser melting additive manufacturing, the newest technique, uses 3D CAD data as digital information to a high-energy laser to create 3D metal parts by fusion of metal powders layer by layer to build up complex parts. Atomized powder is used for its spherical, smooth, narrow size range characteristics. Measuring morphological properties of powders. First, size distribution. This had been traditionally measured by sieve analysis until about the mid-70s, when it started being replaced by laser diffraction light scattering analyzers. Sieves measure the particle width dimension, and laser diffraction measures equivalent spherical diameter, or ESD. Shape distributions have been reported measured by X-ray computed tomography. See reference 1 below. It's a long, tedious measurement and computing technique on small, unrepresentative samples, reporting only 6 parameters on a sample of about 1,400 particles. Now we have state-of-the-art dynamic image analyzers, which can be used to report some 29 different size and shape parameters at up to hundreds of thousands of particles in minutes. Many metal powder properties need to be measured to ensure meeting all specifications. This talk focuses on morphological properties, or sizes and shapes of the powders. Size distribution, measured mostly now by laser diffraction, is just starting to be measured by image analysis as well. And shape distribution can only be measured by image analysis. Some of the other properties measured will be touched on in the next slide. Powder morphology, sizes and shapes, affect important properties of both powders and powdered parts. Rheology includes the flow and mixing characteristics of the powders. Do they flow freely and mix with little internal frictional resistance? Packing density, also tap density or loose pack density, is the bulk density including void volume of a powder in a container after tapping. A higher packing density generally gives a higher pressed and sintered part strength with lower porosity. Level of contaminants affects quality of all types of parts, but is especially important in the laser melting process because of the very thin layer by layer melting technique and the consistent spherical shape required. Green strength of parts. A higher green or pressed strength results in a higher final sintered strength. For porosity, the higher porosity results in weaker green or sintered parts. Sintered strength should be as high as possible, and all mechanical properties of the final powder are affected by powder morphology. The laser melting process uses a rotating mirror which, by following a CAD pattern, directs a laser beam onto the top powder layer, melting the powder layer on top of the previous layer of the part. All particles not melted onto the part are scraped off while the next layer is loaded. Attempts are made to successfully reuse the unmelted particles for as many cycles as possible before it shows too much wear to meet size and shape criteria. It can take 10 pounds of metal powder to produce a 1 pound part if the left behind powder can't be recycled. In parts, this is an example of the complexity of a metal part that can be made by laser melting. Parts can also be very durable, as they're made in one structural piece requiring no subassembly. They're also much more customizable on demand. One machine supplied with a number of different available CAD programs can be used to make individual custom parts on demand, saving the large expense of tooling to produce a single part type. Contaminants can cause point defects in final powdered metal parts made by any method by seriously weakening the part. Contaminants can come from tramp material picked up in processing, from handling, and from packaging later. In large numbers, they can cause parts made by traditional methods to be rejected. But in very small numbers, they can also have a detrimental effect on laser melted parts by the nature of the individual thin layer melting process and the extremely thin layers that can be created. Recycling unused powder per pass is important in laser welding to reduce cost savings on high specialty alloys. The recycled stream has to be remeasured before using again until the powder is out of spec. Powder shape analysis is a very fast and accurate way to identify and quantify the proportion of contaminant particles in the feed material to the laser welder. Every recycled batch has to be first analyzed for its morphology. Powder needs to be recovered and recycled. About 90% of a layer of powder doesn't get welded to the existing part on each pass, even when multiple parts are being layered on the same pass, which is often the case. The excess powder is scraped off as the next layer is being deposited. If the powder isn't recovered, a 1 pound part, again, could end up using 10 pounds of expensive powder, and in order to reuse the unwelded powder, it must be remeasured to ensure the morphological properties are still within spec. Morphological methods for complete method powder characterization. Laser diffraction. Since the mid-70s, when it was starting to replace sieve analysis, this technology has been used in both outgoing QC by the powder manufacturer and in incoming QC by the powdered metal parts manufacturer. Commonly, the equivalent spherical diameter and some of the percentiles of the distribution, like D5, D50, and D90, are measured and reported, as well as a measure of distribution width, like relative standard deviation. In dynamic image analysis, particles flow between a rapid strobe light and a digital camera. A new image of the particles in the camera frame is captured at a rate of thousands to hundreds of thousands of particles per minute, depending on the concentration and the particle size. By knowing the area measured by each pixel and counting the pixels in each image, a very large number of size and shape parameters of each image are calculated and reported, along with the frequency distribution of each parameter and a complete video image file of all particles measured. In a combination system, one particle sample is circulated and measured simultaneously through each analyzer. This allows both the measurement of the industry's tried and true QC measurements by laser diffraction and the new shape measurements made by dynamic image analysis, which can measure and quantify the proportion of contaminants which affect the viability of all powdered metal parts. It also measures and reports shape characteristics which quantify whether or not the recirculating powder charge is going out of spec in laser melting and additive manufacturing. This photo shows the components of the microtrack combination laser diffraction dynamic image analyzer. The pump on the left circulates the sample stream through the image analyzer sample cell and then upward through the diffraction unit's sample cell. Then it returns to the pump, so the same sample is measured simultaneously on these two different technology instruments, allowing reporting of a wide variety of characterization data on the very same sample. To quickly review the principles of laser diffraction technology, smaller particles scatter coherent light at wider angles than do larger particles. The scattered light is collected by Fourier lenses in this three-laser model and is focused on different arrays of diode detectors which measure the intensity of scatter at all angles from 0 to 165 degrees. The scattered light distribution is then mathematically deconvolved to calculate the particle size distribution. This particular microtrack model uses two blue lasers and one red laser at different angles. The blue lasers at lower wavelengths provide the most accurate fine size information. This is a comprehensive sample data report from the software for laser diffraction data. Looking clockwise from top left, there's the detailed tabular size distribution, then the frequency distribution graph, the standard operating procedure or SOP information for the test, the list of percentile data, and the summary data. All information required for traditional QC reports. This is a comparison plot available in the software for comparing size distributions of historical samples on one graph. The comparison plot is a fast way to spot if the recycled stream has become too fine for continued use. Here's a schematic and photo of the dynamic image analyzer. This is a very straightforward measurement technology, but with extremely powerful data analysis after measurement, providing a wide variety of morphological information. Particles flow through the sample cell between a high-speed strobe light on the left above and a digital camera on the right. A video file of the particle images is sent to the computer. All the analysis takes place on the recorded images. The video file is saved and can be remeasured under different SOP conditions. This is the set of parameters MicroTrack reports for its Partan product line, the image analysis line. Rather than go into each in any detail, I'll describe in 4 general terms what they measure. First, of course, is size. We give you 15 different size measurements of each particle in various diameters, lengths, widths, thicknesses, and more. The last 3 columns here are shapes of different natures and are generally expressed as ratios of size parameters. Form factors include a number of different parameters that indicate how closely the particle is to being a perfect sphere, or various aspect ratios or elongations of the particle. Surface roughness parameters are just that. 3 different parameters can indicate the roughness factor of the particle's surface. Other specialty parameters report the overall light intensity coming through the particle and the curvature of the particle as a gradient of light intensity. dA, highlighted above under size, is a size parameter. It's the area equivalent diameter of the particle, which closely correlates to the equivalent spherical diameter reported in diffraction data. Circularity is a form parameter. On a scale of 0 to 1, 1 is a perfect circle. Circularity is affected by both surface roughness and aspect ratio. See the particle image in the center. The width to length aspect ratio, on a scale of 0 to 1, 1 is a perfect sphere. Elliptical forms would be less than 1. Convexity is one of the surface roughness parameters. On a scale of 0 to 1, 1 is a perfectly smooth surface with no concave indentations. Transparency is a measure of the light intensity transmitted by the particle. A higher transparency indicates a more translucent particle. The particle image shown in the middle is an elongated, rough-surfaced, and translucent particle. Any of those morphological qualities can indicate contaminants and be quantified as percent of sample. This is a view of the XY graph and tabular data display for the dynamic image analyzer. Up to 6 different size and/or shape parameters can be displayed at one time for one sample. In the display here, we're plotting the dA, the area equivalent diameter, as a differential frequency distribution. See callout 1, the red curve. The green curve, 2, is plotting the width to length aspect ratio for each of the size fractions plotted for dA. The y-axis on the right side of the graph is the width to length scale, 0 to 1, 1 indicating a perfect sphere. In the scatter diagram display to be discussed later, the shape parameters are plotted in frequency distributions for all particles regardless of size. Callout 3 in this display points to the data in the graph and the table, indicating that the dA size fraction from 110.6 to 127.6 microns has a width to length ratio of 0.89, and that size fraction makes up 23.28% of the volume of the entire sample. This is the View Particles display. It's the workhorse display window for the DIA analyses where post-measurement analysis supplies many answers. The complete image file can be viewed. The particles selected in callout 1 in the image file and in the frame above in blue boxes have all the size and shape parameters reported in the table callout 2 in the upper right. The scroll bar indicated by 3 is used to increase the lower window to display more images. The Search Particles button, callout 4, brings up a window which allows searching for groups of images with user-defined size and shape parameter limits. 2 searches have been set up in the window to the right and will be discussed in the next slide. More features in View Particles. Here many more images are being displayed. The Search button has opened the Particle Query window, callout 1, where a search with 3 criteria has been entered. Images with DA less than 50 microns, circularity less than 0.8, and width to length ratio less than 0.8. This will isolate images of the smaller particles, which are non-circular and oblong. Note in the highlighted search, callout 2, this group of particles make up only 0.09% of the entire sample volume and about 5,000 particles by count of about 25,000 in the sample. And note in the search listed above the highlighted one, where the width to length criterion is left out, this group made up 0.34% by volume of the sample and had a count near 14,000. Multiple searches can be set up and chosen to use as desired. The image file will only contain images of the particles searched for after the search is conducted. The DA was included in the criteria to illustrate that various shape criteria can be searched for within a particular size fraction, as well as for the entire sample. The Scatter Diagram button, callout 3, when selected, will bring up the display in the next slide. The search criteria selected for will cause the scatter diagram to display only the particles searched for. The scatter diagram is the blue graph above, and it displays the location of every particle searched for in the previous highlighted search, relative to the parameters selected in the X and Y axes in the red distribution graphs above and to the right of the scatter diagram. The number of particles, callout 1, is the number that were included in the search. Any of the different size and shape parameters can be chosen, callout 2, to be displayed in either the X or Y graphs, and the scatter diagram will include the location of each particle relative to the parameters chosen in the graphs. Summary data for the X and Y parameter distributions are listed on the right. The distributions can be plotted in number or volume percent, and areas of the scatter diagram can be isolated to report results for only that area. And a general feature of the software allows copying of all graphs directly to clipboard and all tables exported directly to a spreadsheet. This makes report preparation fast and easy. Here are some more important features of the scatter diagram. The view in the upper left has the DA on the x-axis and the width to length ratio on the y-axis. we see two distinct size modes in the X graph, greater and less than 50 microns, almost completely separated. The D50 percentile is 0.85 for the width to length ratio in the entire sample. Areas within the overall scatter diagram can be isolated and evaluated. In the lower left view, we've used the cursor to isolate the large size area, greater than 50 microns. The resulting subdistributions of dA and width over length are now displayed in the X and Y graphs. The D50 for the coarse mode has a W over L ratio of 0.92, indicating much more spherical particles in that mode, which by volume distribution is over 95% of the sample. The view in the lower right shows the statistics on the fines fraction. The width over length D50 is a very low 0.78. One might come to a quick conclusion that the fines are contaminants and the coarse fractions are good spherical particles. But this is just a simple example, which however does show the power of the image analysis software. Typically, a number of different searches would be made and evaluated to reach a well-informed decision about setting up the optimum filters for the SOP. But here there is the flexibility and power to do it. Any query can be automated in the SOP as shown in the filter function display above. One can choose individual C columns F1, F2, and F3 parameters at callout 1, or they can choose combinations of parameters, columns F4 and F5, callout 2. Filters for any one or combination of the 29 parameters can be set. When this OP is used on a sample, then, any one of these filters can be quickly applied to the result of the entire sample measured. This slide shows a feature in the DIA software which allows the easy, convenient tracking of any parameters from consecutively run samples. It's the perfect way for tracking key changes in sizes and shapes in the recycled streams in laser melting. Both size and shape parameters can be tracked here to indicate when any key parameter goes out of spec, and the stream can no longer be recycled for use. Control limits for the specs can be set on the charts for ease in decision making. Images can be captured and copied. Here are two different contaminant particles with low circularity and low convexity. The image on the right, selected from the frame in the View Particles display, automatically lists all parameters for that particle to the right. Key contaminant parameters are listed under each image. Image analysis technology is the only one that can provide this kind of information. In summary, sizes and shapes of metal powders need to be measured to meet suppliers' and users' QC needs, to identify and quantify contaminant particles for all processes, and to monitor recycle streams in laser melting additive manufacturing. Laser diffraction is the size technology used in the industry for QC. Dynamic image analysis is the technology used for morphological data. A combination laser diffraction dynamic image analyzer can now be used to make both measurements simultaneously on the same sample in a matter of minutes. Up to 29 different size and shape parameters are reported, and key powder parameters can be identified and quantified. And that sums up our webinar for this morning. Jason, I'll turn it back over to you for some announcements and a Q&A session.
Thanks for checking out this on-demand presentation. We invite you to send samples for complementary analysis so we can demonstrate our ability to improve your product or process by measuring size and morphology. Please send an email to the address on your screen to get started. We're also happy to schedule an on-site or virtual demo.